So again, welcome back to our latest lecture session. So again, let's have our customary review of what we have been up to in the last couple of sessions. So I guess we have been discussing about the reduction potentials and the standard reduction potential, yes. And I guess we have been able to now understand what it is that I need to understand. Let's say when I look at PE or PE naught, and let's say when I look at two half reactions, let's say, right, the half reactions written as reduction, let's say, which is the way standard half reactions are written, right. I then can by comparing the PE values, right, go about finding about, let's say, which reaction will stay as reduction and which reaction will proceed as oxidation, right. So again, let's try to quickly summarize again what we have been up to. So we looked at, let's say, developing the relevant equation for PE, that's equal to PE naught minus 1 by n log Q dash, right. And this particular equation we derived from our particular simpler example of A oxidized form plus n electrons going to its reduced form, right. And obviously n here is the number of electrons being transferred here, and Q dash, what is that? Nothing but activity of the reduced form by activity of the oxidized form of the compound, right. So again, then once we looked at this particular what is the equation of PE, right, we then looked at the relevance of PE naught, and then also looked at how I can understand the system by looking at, let's say, the variables PE minus PE naught, right. For that particular example, we tried to draw the analogy with respect to the acid base reactions, yes. So I guess for the acid base reactions we had something like, let's say, HA can deprotonate, right, H plus plus A minus, or written as this particular form, right, HA, right. So similar to our particular equation here, right, which is nothing but n electrons plus A oxidized form goes to the reduced form. As in here it's the compound with the without the proton, here it's the compound without the electron, here it's the compound with the proton, here it's the compound I guess with the electron, right. Again, that's obviously layman's terms, but helpful in understanding the relevant system, I guess, right. So in that particular what do we say example, let's say, we started looking at the relevant aspects with respect to the graph of PE, right, with respect to the concentration of the either the oxidized form or the reduced form of the compound. I guess let's again look at that particular graph here. So here we have PE. Obviously when you have H plus involved in that particular half reaction, then you are going to have the reference to be PE naught minus NH by NPH, right. Let's say for this particular case though, it's only going to be PE naught, obviously, right. So obviously let's say when PE minus PE naught, let's say, is low, right, what does that mean? That means the activity of the electrons is going to be relatively high. So what does that mean? Obviously looking at this half reaction again, if the activity of the relevant electrons, let's say, is relatively high, right, the theoretical activity obviously, right, then obviously the reaction would proceed to the right, thus the reduced species would predominate, and thus we see that the reduced species or A reduced, which means with the electron, is going to predominate in the region PE less than PE naught, right, and obviously that's the reference here, right, in this particular region. But obviously in the other particular region where PE is greater than PE naught, or when PE minus PE naught value is high, what do we see here? Obviously, the inverse of what we discussed earlier, right, or the converse, let's say. So we have low what do we say expected activities of the electron, thus what does that mean now? So again oxidized species would predominate, right. So low values of, or low what do we say concentrations of these particular electron, right, meaning the reaction to the left would be what do we say preferred. Again, this is for your particular understanding, right. Again, obviously these are half reactions, when we talk about activities of electrons, right, you do know that these are more or less, let's say, the probable values or theoretical values, because from our background we do know that electrons would not exist in solution, right, or they will not accumulate in the solution, yes. Again, so obviously when we have low what do we say activities of the electron, oxidized species would predominate. So that's why in this particular region we see that the oxidized form or the compound without the electron would predominate, right. So this is obviously similar to our particular acid base relevant chemical process, where on the left hand side of our pK, I guess, right, we have our protonated form or with the H plus, and here in this particular region again we have the deprotonated form or without the H plus, right. Again, that is for your particular understanding obviously. So, let us move on to what we looked at. Then we started looking at, let us say we had two half reactions, I guess, right, let us say 1 and 2 half reactions, and we have the PE1 and PE2 for these particular half reactions, let us say. Then we looked at ways to be able to understand which particular half reaction will go through as reduction and which one would go through as oxidation. I think the example we considered was similar to, right, A oxidized plus N1 electrons goes to A reduced form, and here B oxidized plus N2 electrons goes to B reduced form, right. So, obviously here both the half reactions are written as reduction, right, but for obviously a redox process to go through, you need both an acceptance, right, and also donating of the electron, right. So, both gain and loss of the electrons, but here obviously it is only a gain of the electrons. So, obviously for the redox process to go through, one of these will need to go through as oxidation and the other will stay as reduction itself, right. So, obviously to compare that, I guess we looked at a relevant example and or the derivation, I guess, right. We came up with some equation like P1 minus P2, right, is equal to 1 by N1 N2, right, N1 and N2 being the number of electrons being transferred, right, say in each half reaction, right, say, right, and log K by Q, right. So, after looking at this particular equation, or we can look at it right now again too, what happens when K is greater than Q? So, this term is positive, K greater than Q, meaning Q less than K, right. So, obviously what do you see here? You see that this term is going to be positive, or P1 minus P2 is going to be positive. So, obviously when Q less than K, right, what does that mean? The reaction would proceed as written. And how did we write this particular what do we say equation? If you remember, we said that this would proceed as reduction, and obviously it is negative here. So, this we considered would proceed as oxidation, right, and then we came up with this relevant particular equation, right, and then we look at the relevant K and Q values and so on, and from this relationship we can see that this particular term is positive obviously when PE1 is greater than PE2, right. So, PE1 greater than PE2, right. When P1 greater than P2, what do we see? That the first half reaction will go through as reduction, right, and the second one will go through as oxidation, right. And then to be able to better understand this particular aspect that we looked at in what is our derived at, we looked at a relevant particular figure here, right. And obviously here we have a case of two redox couples, A reduced and A oxidized, B reduced and B oxidized, right. So, and then we chose one particular case when obviously PE2, I guess, let us say if I am starting from somewhere out here, right, and from here let us say PEB, and this is for A here. So, let me choose this particular point, right. So, we start out with a case obviously as you see here where PEB is greater than PE of A, right. So, that is what you see here. But we looked at both the scenarios as in what would happen if let us say B goes through as oxidation and not as reduction, as in from this particular case we know that the redox process would go through in such a way as B would see reduction, would go through in this particular half reaction, and with respect to A it is going to be oxidation, right. That is what we see from this particular or understood from this particular equation, right, looking at the K by Q values and so on here. But to be able to better understand the system, we looked at that particular case when we considered that okay, let us see what happens when oxidation goes through it with respect to B, I guess. So, let us see that again, let us summarize that again. So, here let us say if oxidation goes through, what would happen here? Let us say if oxidation goes through, as in this is the reverse reaction, let us say, then the oxidized form of the compound will increase and the reduced form of the compound will decrease, right, as in here this is what you see. So, this oxidized form is going to increase, right, and obviously this is the reduced form which is going to further decrease, right, if B goes through as oxidation, right. So, what does that mean? That PEB is shifting here to the right, right, and obviously then if B is going through as oxidation, A needs to go through as reduction. So if it's reduction, obviously A reduced form will increase in concentration, so that means this is what you are going to observe, right, and obviously the oxidized form of A is going to decrease in concentration, right, so it's going to go through in this particular direction. So obviously PEA will shift further to the left, and obviously as you see, right, PEB and PEA do not approach each other, or they are moving away from equilibrium, right. So that is obviously not what you would see out there in the nature, right. So you would obviously see that, or the system tries to travel in such a direction that PE of A and PE of B are same, meaning the system reaches equilibrium, right. So what is it, what happens here when PE1 and PE2 are the same? That means K and Q, right, are the same, meaning the system has reached equilibrium. But as you see, if PE1 travels in one direction and PE2 in the other, right, as we see in this case when we consider that B would go through as oxidation and A would go through as reduction, for that particular scenario when PE of B was greater than PE of A, right. So we looked at that particular example and we saw that, right, the system was not approaching equilibrium, right. So that is what we see. So obviously I guess we will look at the other case, PEB is greater than PEA obviously still, but now we are going to go by what we understood earlier, right, that B will go through as reduction and A will go through as oxidation, right, and let us see if this makes sense, right. So obviously if B is going through as reduction, right, the reduced form of B would increase in concentration. So right, this is the reduced form, right, so this is going to increase, right, and the oxidized form would decrease, and so it will travel in this direction. So what does that mean? P of B is going to travel in this direction, and with respect to A it is going to be oxidation, right. So the reduced form of A concentration will decrease and the oxidized form of A concentration is going to increase, right, in this manner, right, and reduced form is going to decrease in this manner. What does that mean? PA is going to shift towards the right. So in this particular case, right, when we saw that, let us say for the case of PEB greater than PEA, we consider, let us say B goes through as reduction, A as then as oxidation, you then see that the system approaches equilibrium, right. So that is what obviously goes through. So obviously we looked at it in two aspects, one with respect to the equation PE1 minus PE2 equal to 1 by N1 N2 log K by Q, and also visually I guess, right. So then we started discussing the relevant aspects I believe with respect to application of PE values. So we are going to skip that and move on to what we some of the applications here I guess. So now let us say we are going to consider cases, let us say when let us say we consider only let us say the redox process, what would be the PE value and what would the PE value be considering all the relevant chemical process we have discussed thus far, right, as in complexation, precipitation, dissolution and acid base, right. So that particular what do we say analysis now that we are going to do over a couple of sessions, right, is going to give you a clearer picture of the relative importance of each of these processes we have discussed thus far, right. So before we go further, I guess we are going to look at a few standard what do we say redox potential tables. So here obviously let us pay attention to these particular names here, right. And so obviously here we have ozone, chlorine, hydrogen peroxide and so on. I guess people with SEM background will know that they are oxidants, right. And here you have ferrous iron, sulfide, hydrogen and so on, and dithionite, let us say people with background will know that they are reductants or reducing agents, right. But let us say let us say you do not have that background, so how will you let us say be able to estimate let us say which particular compound would act as a reducing agent in general out there in the nature and which one would in general act as a oxidizing agent. So for that particular aspect I guess you are going to refer to your P naught value here, let us say, right. So here you know the P value is positive and pretty high. So what does that mean again, right, that the reaction strongly favors going to the right. P naught, if you see remember what was that, it was nothing but equal to 1 by N I believe log K, right. P naught value we define it as 1 by N log K if you remember the relevant, or if you can recall the relevant derivation. So greater P naught means greater the value of K, right, and we know K is nothing but activity of the products rise to the relevant stoichiometry by activity of the reactants, right. And obviously if you look at that, a greater value of K means this reaction would go through in the or go to the right, right. So obviously reduction is going to take place, right, as in this particular compound would act as a strong electron acceptor, right. So electron acceptor we know is an oxidant, right. So obviously when the P naught value is high, meaning K value is relatively high, what does that mean? That the reaction would go through or prefer to go through in this particular direction, right. And thus what does that mean? That this in this particular case O3 ozone, right, we can understand that it's a strong oxidizing agent. So when someone refers to, let's say, a particular compound as a strong oxidizing agent or a strong reducing agent, keep in mind that they are all relative, as you can see from these particular tables, right. So for example, ozone, among the relevant oxidizing agents listed here or oxidants listed here, you see that's remarkably what do we say, strong oxidizing agent, right. So obviously compared to, let's say, chromate, well, that's not a great example, or compared to oxygen, you see ozone, let's say, right, is a much better or strong oxidizing agent, right. So while here P naught value is 21, here it's around 35, but keep in mind that here we are talking about logarithmic values. P naught is 1 by n log k. So fact, let's say a difference here we have, what do we say, differing by 10, right, that means it's a considerable difference here, right. So keep that in mind, that P naught values are 1 by n log k, so you need to look at the logarithmic scale, right. So obviously reductance, I guess, right. So here I guess it doesn't give you a great picture, as in this particular system seems to be a bit messed up. So obviously if it's negative, right, what do you understand if it's negative now, right, say, so P naught is equal to 1 by n log k, and if P naught is negative, right, what does that mean? That K value is pretty less, right, or less, let's say, relatively less. So if K value is less, what does that mean now? The reaction to the left will be favored or will proceed, right. So the reaction to the left, and in that case what do you see? That it is going to be oxidation, right, or the relevant compound here would act as a strong electron donor or a strong reductant, right. So but obviously I guess P naught doesn't give you the true or accurate picture. So for that particular case we have, I guess, looking at a particular system where, let's say, we consider the relevant activities of these compounds, let's say, which are involved in your half reactions to be 10 power minus 3 and to the pH to be at 7, and then I guess you can look at the P values, right, for that particular hypothetical scenario, which more or less would be similar to what you would expect in nature. We are choosing 10 power minus 3 as in relatively low concentrations, but not too low as to be hypothetical values, right. So we are now going to look at what do we say, P values rather than just P naught. The P values we are going to consider, I guess, is when, let's say, at pH 7, right, and also when all the other activities are equal to 10 power minus 3. Yes, so we are looking at this particular calculation for Pe, right, which is equal to P naught minus 1 by n log activity of the reduced form by activity of the oxidized form, right, and obviously if we have any other elements too, I guess, right. So anyhow, for that, from that particular scenario, or for that particular scenario, we now have the P values, right, and obviously this will also take into account the effect of pH, right, and so this will obviously, or this particular set of data will give us a better idea about trying to understand which particular compound, let's say, would act as a oxidant and which one, let's say, would act as a reducing agent, let's say, for example, dithionite here, right, dithionite here, yes. So how do I go about that now, right? So unlike P naught, right, which is 1 by n log k, right, this gives me an idea about the system at let's say equilibrium, right, or obviously when the activity or theoretical activity of the electron, let's say, when all the other activities are equal to 1, right. So again, why do I say so? Because we know that P equal to this particular case, right, and obviously what is this now, when activity of all the other compounds is equal to 1, you see that P equal to P naught. So again, that is what we just understood here. So P naught equal to 1 by n log k, right. So we can understand this particular case as in, let's say, which one would be a strong oxidizing agent or such. But with respect to looking at Pe, let's say, now I can compare Pe1 and Pe2 of any two half reactions, let's say. So for example, let's look at this particular ozone and let's say nitrate here, right. So if I consider these two half reactions, I see that Pe1, which is 27.4, right, is greater than Pe2, and what is Pe2 here? It's 6.14, right? So again, what does this mean? This will help us understand that ozone, right, will oxidize ammonia to nitrate, right? And how did we come about that? Again, we looked at the relevant derivations and such earlier. So here, by looking at the two PE values, right, for this particular scenario when pH equal to 7 and the activities are equal to 10 power minus 3, we see that we have this particular PE for ozone 27.4 and 6.14 for the nitrate relevant half reaction. So by comparing the two PE values, I see PE1 is greater than PE2, right? So obviously, what does this mean? This particular reaction will go through as written, right, or would proceed from left to the right, right, while this will proceed from the right to the left, or this would not go as reduction, but will go as oxidation, right. So here we have reduction, right, gain of electron, oxidation. Here we have the loss of electrons if this is reverse, yes. So that is what you will observe. So in any such scenario, when you compare let us say the PE values of any two compounds, let us say, so here permanganate, let us say, and let us say any compound here, let us say ferrous iron, right, you will know that PE1 is greater than PE2, right. So permanganate reaction will go through as this particular case, right. So our MnO4 minus will oxidize, let us say, right, Fe2 plus 2, where do I look at? So let us say for this particular case, Fe2 plus 2, FeO is thrice the solid, right, yes. So that is what obviously you would see here. So again, what is the whole point behind it? So the system would try to reach equilibrium, right, as in PE1 and PE2 would travel in this particular direction, as in they would try to reach equilibrium, right. And when will we reach equilibrium? When PE1 decreases obviously in this case and PE2 increases in such a manner that finally we end up with PE1 is equal to PE2 and we end up reaching equilibrium, right. So let us just try to understand that obviously again. So looking at those tables, I can compare for any particular cases, let us say PE1 and PE2, and once I identify which particular PE value is high, let us say PE1 is higher than PE2, right, for that ozone and ammonia relevant half reaction. So what happens now for the system to reach equilibrium? You know that it should be PE1 equal to PE2, right. So for that to happen obviously, and we looked at the relevant figure 2 earlier, right, we see that PE1 has to decrease and PE2 has to increase, right, and until PE1 is equal to PE2, right. So obviously again PE1 will have to proceed as reduction and PE2 will have to proceed as oxidation, right. So we are going to look at this particular case of reductive dechlorination of carbon tetrachloride, right, or perchloroethylene here, right. So here I guess the relevant aspect is that these chlorinated solvents, so let us say, are toxic to humans. So obviously you want to be able to either remove them, right, either by phase change or let us say by actually degrading it, right, or in this case degradation would mean reduction. Why would I say reduction? Obviously, right, we know that here carbon bound by the Cl minus, let us say, or Cl, right, you know Cl is relatively more electronegative than carbon, right. So you know that carbon here is obviously going to then be in the oxidized form. So here we are going to look at reductive dechlorination, and for that obviously I need a reducing agent, and in that case here obviously my reducing agent is Fe2 plus here, right. So again here we are going to look at the relevant aspects, let us say with respect to redox chemistry, right. But the major aspect that we are going to try to do, or look at, let us say with respect to the last couple of sessions, pardon me, is that we are going to try to bring in the knowledge of the previous major aspects, as in acid bases, complex formations, and what else, precipitation and dissolution, and how they go hand in hand with the relevant redox process, right. So until now we looked at the 4 major aspects relatively independent of each other, while we did look at a few examples which try to look at the preceding aspects, right. Here we are going to bring everything in, right. So here we are going to look at it phase wise, as in what would be the scenario you would expect, let us say, if only one aspect is considered, and then look at what happens actually out there in the nature, right, or what happens out there in nature, and how that compares with your particular case or the theoretical aspect that we look at if only one particular process is considered, right. So let's go through, I guess. So we are going to obviously look at reductive dechlorination of perchloroethylene, right, by ferrous, right, and here we have the relevant half reactions and the relevant P naught values. So here let us say I am going to start with the assumption that all the activities are going to be equal to 10 power minus 3 and that the pH is equal to 7, right. So let us say the PE for the first half reaction, right, P1 is going to be, as you know, equal to P naught minus 1 by n log Q dash, right. So that is nothing but equal to P naught here. Why is that? Because Q dash for that particular half reaction, right, 1 is activity of Fe 2 plus by activity of Fe 3 plus, right, because both the activities are the same, Q dash is equal to 1. So that is why P1 is nothing but 13.03. So the second case, right, P2 it is going to be equal to P naught minus 1 by n log Q dash for this particular half reaction. Let us write that down. P naught is 10.84 minus 1 by 2, and why is it 2? Because 2 electrons are being transferred here or being accepted here, right, log Q dash as an activity of C2HCl3, right, the reduced form plus, not plus, pardon me, into Cl minus by activity of C2Cl4, right, into activity of H plus, right. So let us plug in the relevant values here. So that is going to be equal to 10.84 minus 1 by 2 log activity of this particular compound, which we know is 10 power minus 3 based on our assumption, 10 power minus 3 into 10 power minus 3 by 10 power minus 3 into, but H plus we know that pH is assumed to be 7 into 10 power minus 7, right. So here we are going to look at the relevant values. So 10 power minus 3 cancel out. So I am going to be left with 10.84 minus 1 by 2 log 10 to the power of minus 3 plus 7, 10 to the power of 4, right. So that is going to be equal to 10.84 minus 4 by 2 is going to be equal to 2. So that is going to be equal to 8.84, right. So let us look at or summarize what we have been up to here, right. So we looked at the case, or we are trying to look at dechlorination of C2Cl4 by ferrous, and then to look at the relevant particular aspects, right. We calculated the PE1 and PE2 values, and here though we see that the PE1, right, is greater than PE2, right. So the PE1 is greater than PE2, right, and what does this mean? You know that then the first half reaction will go through as reduction, right, and the second half reaction goes through as oxidation, right. As in, what do we understand? As you know, the relevant what do we say case we had was Fe3 plus going to Fe2 plus for the first half reaction, and C2Cl4 being reduced to C2HCl3 in the second half reaction. Obviously I am not balancing it out with respect to H plus and the electron transferred, but these are the couples, right. But here, as you know, because PE1 greater than PE2, let us look at the values, I guess, 13.03 and 8.84, right. So what does that mean? Obviously that Fe3 plus is going to be reduced to Fe2 plus by C2HCl3, right, but this is not what we expect or see out there in the nature now, right. So again, what is the reason here, right? The reason here being that you know that ferrous or ferric can form complexes, not can, will form complexes or aqueous complexes out there, right. So that is one aspect we certainly haven't looked at or considered, right. So I guess today, let us say we understood the particular case that you would expect, let us say, when you consider ferrous or ferric, right, say as what do we say, just the free metals, without considering the case of the possibility that the complexes will be formed, which you know does happen, right. So here we, until now, let us say the past 5 minutes we looked at this theoretical case when let us say we do not have the other chemical process, we only have the redox process occurring, and in that case do we see what do we say, reduction of C2Cl4? No, we actually see, what do we see here, this is going to go through as Fe2 plus is what do we say, Fe3 plus, let us say, is reduced to Fe2 plus by C2HCl3. That's what you see. Why is that? Because Pe1 is greater than Pe2, right? So in the next couple of sessions or next session, right, we are going to look at that particular case when we consider, let's say, Fe2 plus and Fe3 plus can form aqueous complexes, and then we are going to look at calculation of the actual, what do we say, concentrations of these Fe2 plus and Fe3 plus metals or free metals that would be in equilibrium with the complexes in the solution, and then calculate the Pe values, right. So I guess for now we looked at case 1, let's say case 1, right. What do we say, only redox, right, and we see that Pe1 greater than Pe2, right. What does that mean? That Fe3 plus is reduced to Fe2 plus by C2HCl3, right. That is what we see, because P1 greater than P2, this will go through as reduction, right, and this will go through as oxidation, as in this particular compound will act as the reducing agent to reduce Fe3 plus to Fe2 plus, right. But why is that? Because we consider the case that only redox process occur. So in the next couple of cases, right, we are going to consider the case, let us say, when we also have complex formation and redox, and then calculate P1 and P2, and then try to understand the system accordingly, right. So I guess with that I will end today's session, and hopefully with the next session you should be able to get the holistic approach, right, or understand the holistic aspects that are involved in this particular scenario, right. So and I guess with that I will end today's session, and thank you.